All right, thanks guys. Hello and welcome to today's webinar. I'm pretty excited for this one today where we're going to talk to you about how we can use simulation for 3D printing to confidently build strong parts. Before I move on from this slide, I do recognize that this title is probably way too long, but I'll do my best to justify the long title as we go through this. So a quick look at our agenda today. We'll start by introducing a demonstration part, which is an existing metal part that we're trying to improve and replace using 3D printing. From there, I'll give you an introduction to the technology we're working with, and that sort of includes a quick look at the simulation landscape and why simulation for 3D printing is so new and exciting. We'll take a quick look at the printers involved as well. Then we'll switch over to defining the forces involved with our demonstration part, because that's going to provide us with values that we need for our simulation. This third bullet point was definitely my favorite, so stay tuned and I'm sure you'll see why. But once we have that, we know what forces are involved, so we can design our part and put everything together by simulating the forces on that part and using it to optimize it and sort of redesign it as we need. So once we have that, we can finally move on to printing it and testing it out. And I wanted to talk about the part first because I think the part really highlights the problem that 3D printing simulation solves. So when it comes to the part, we work with manufacturing facilities. We've been doing it for 40 years. We get hands-on with the solutions that we offer, but we don't have a manufacturing facility ourselves. So sometimes when a new product comes out, we get to find applications outside of manufacturing. And I think this part on my motorcycle is a good example of that because it really mimics the applications where we see 3D printing thrive. And that's a metal part that deals with a decent amount of force, but I want to improve and replace it. So it's also in an environment where I can't afford a failure, so I need something really strong and I need to have full confidence that it's going to work. So here's the bike. This is a Yamaha XSR 900, and if you've ever ordered material from us, there is a chance that it was delivered to UPS on the back of this bike. But I love this thing. One of the things that I love about it is that it's comfortable enough to ride up to these mountains in Arkansas, but it also handles really well, and it's a lot of fun to ride once I get there. So it's just great all around. But the problem that I have with it is sort of related to that. And it's definitely self-inflicted, but the issue I have is with these brackets that mount the headlight. So there's one of these on either side, and functionally, the brackets work just fine. They mount to the frame using these two bolts. It mounts to the headlight using this third bolt up in the front, and it goes into the headlight bucket where it holds this thing. There's also a little tab that comes into the back of the bucket that keeps it from rotating around. Additionally, it holds the turn signals here, and then it mounts the windshield using these two threaded holes that are on the inside. And that windshield is great for those long trips. It looks small, but it actually does a decent job of pushing the wind sort of out of the way, especially for long, drones on the highway. So I'd like to have that thing, but it's 100 degrees here in Texas some days, and I like to take this bracket off. Sometimes I like to just switch things up, and so I find myself taking this thing on and off quite a few times during the year, and that's where my issue lies. So to take this bracket off, I have to get to these little Allen head bolts that are in here, but as you can see, there's not really enough space to fit a tool in there, and even if I could fit the tool in there, there's not enough space to get these bolts out. So you'd think it would be as simple as, maybe removing these two screws and like rotating this whole assembly, but then I'm juggling the headlight and the turn signals and this bracket on both sides. So the next best option, I could unscrew just this bolt, move the headlight out of the way, and then try to get to the bracket from there, which highlights another issue, which is that inside of the bucket, there's a nut and it's not captured at all. So if I try to loosen this nut will either just rotate inside of here, or it will loosen and it'll fall off inside of the headlight bucket. And now I've got to take these screws out, pull the headlight out of the bucket, and again, I'm left with multiple parts that I'm juggling and removing multiple screws. So it's just become this huge ordeal anytime I want to change this thing out. and I really want to redesign it so that it resolves my issue. And while I'm doing that, I can resolve a much smaller issue, which is that I've painted, printed, and vinyl wrapped a lot of the trim pieces on this bike black already. So the bracket sort of stands out now, and it's kind of bugging me. So I've convinced myself that this was all worth it. So hopefully you've been convinced as well. But I've been wanting to print one of these parts for a while now. But unlike the other ones I've worked on, this part has to be really strong and not just hold the weight of the headlight, but it has to hold it while it's amplified during riding, which is cornering, bumps, braking, acceleration, whatever. I want to have the confidence that it's going to survive what I'm going to throw at it. So I know I could make some big, expensive monstrosity that's filled with carbon fiber, but I want it to be sort of small and sleek and look good. And I don't want to spend crazy money because our marketing budget isn't that big. So I've been reluctant to print this thing so far. Uh, and in my case, some of that is for aesthetic reasons. But if you're in the manufacturing floor, you're probably going to have constraints on size or shape or weight because typically you're working with a small part of a larger assembly. So it has to have clearances to fit within that assembly, and it also has to be strong enough to survive. And when it comes to strength, we make a lot of claims with these printers we sell that they embed parts with carbon fiber. So you get these super strong and small parts, but a lot of the time in that workflow so far, you're going to be designing and printing and then maybe physically testing the part in some sort of apparatus beforehand, or maybe you just throw it straight in and see if it breaks. And then you go back through the whole process and see if you need to make some changes and then reprint the part. So what if there was a way to save that money for those prints to begin with and save the time spent printing and testing before the print ever comes out? So that's where simulation comes in, and hopefully that sort of explains the benefits of it before we dive deeper into this. So with that understanding, let's take a quick detour and we'll talk about the technologies we're working with. So we'll quickly cover the sort of simulation landscape, and that'll help us discuss why none of those options have really worked for 3D printing until now. So quick Google search is going to give you a huge list of existing softwares out there that have simulation capabilities. We work with SolidWorks here, and my unbiased opinion is that it's a great option for that. So diving a little deeper, inside of simulation, there are even more options for simulation types. So, whether it's fluid flow or fatigue life or thermal properties, the list goes on, but probably the most common type is going to be a static analysis. And so within SolidWorks, this is sort of what it looks like. This is a screenshot from one of our simulation YouTube videos. If you're interested in this stuff, definitely I would encourage you to go check those out. There's some really great stuff there. But in a static simulation like we've got here, we use our CAD model, which has defined dimensions and a defined material that the part is made out of. The material is important, of course, because something like rubber would behave much differently than metal, obviously. And then once we have all of those things defined, we take our part and we fix it by some sort of feature or features. So in this case, we've got these bolt holes. And then we apply a designated force to another feature in a specific direction. And we get to see how and where the parts react. So we get a few different outputs from this, including stress and strain. One of the more useful ones is going to be your displacement from the original position. And you get this sort of exaggerated look at where and how it's going to be displaced. And so this is all well and great. And as much as I love SolidWorks, there's a common fault with it and all of these softwares when it comes to 3D printing, especially when it's FDM 3D printing. So to understand that fault and make sure we're on the same page, we'll look at a 3D printing, just FDM really quickly. So FDM printers, they melt plastic and they build a part up cross-section by cross-section or layer by layer. Markforged printers take that a step further and they add the capability to embed your plastic part with these continuous strands of fiber. And within that, we get this huge amount of strength. So this is a part embedded with carbon fiber. We've got 22,000 pounds. So it's awesome and it's incredibly useful, but it highlights one of the problems when it comes to simulation. The simplest way to put it is that these parts don't have uniform strength throughout. So part of that is by design. After we've created our SolidWorks CAD model and we bring the part into our slicing software, which is specific for the printer, and it basically tells the printer how to build the part based on our print settings. In the slicing software, we actually get to customize where the fiber is routed, which is one of the problems. So the second problem is that we don't typically solid fill our parts. We use some sort of infill shape and density, and that decreases our print time and weight without a huge reduction in strength. But again, it's this sort of non-uniform strength. And then the last issue when we come to simulation is that parts are slightly weaker between the layers than they are within one layer. So there's not really a way to make all of these changes in our slicer and then bring it back into the CAD software for simulation. So to solve that issue, we bring simulation into the slicing software. So Markforged brought simulation here, and now we can lay out our print parameters and then simulate the forces. So circling back to our headlight bracket, we're going to take advantage of this new software and use it to build our part and test its strength before printing. But like we talked about earlier, when it comes to simulation, we need a few inputs. And for the sake of this webinar, I'm going to keep things relatively simple, and we'll worry just about the vertical force on this bracket from the headlight and the force that it encounters during riding. I really just want a ballpark value to plug into the simulation. So the first thing we need is going to be a fixture point or fixture points, and that's something that locks this part into place. So for the headlight bracket, pretty straightforward. We've got our two mounting bolts. And then the second thing we need is our applied force and the direction of that force. In this case, again, there's a couple of things acting on this part, like the wind pressure on the surfaces, the pressure from the bolts clamping down. There are perpendicular forces to this face during cornering when the weight sort of transfers. The list goes on. But again, I'll focus on the weight of the headlight bracket that the headlight that these brackets have to carry. So we can apply that weight to this third bolt hole, and we know gravity is pulling it downwards. So we need to know this force for simulation in terms of newtons or pounds force. Right now, the simulation software just takes a newton input, and it's easy enough to convert after doing all the math, but I'll go ahead and just use metric to keep things straightforward. And the math is pretty easy. I'm sure most of you are familiar with this concept, so I'll try to spare you too many details, and I promise towards the end of this, it'll get more fun than just doing math. So for anyone who's not familiar, the equation for force is mass times acceleration. So starting simple with the bike sitting still, I can weigh the headlight to get the mass, and I know it's accelerating by 1g. And so g is a constant number. It stands for the acceleration of gravity, which in metric is 9.8 meters per second squared. But in this case, that force is divided between the two brackets. So that's easy enough to do. We can just divide by 2. But that really leaves just one last thing, which is that 1g means there's no movement. So this bike isn't just going to sit in the garage. I like to ride it all over the place. So I really want to find a way to find that value. And the suspension helps, but there's still going to be increased g-force on this thing during riding. And I really need a way to measure that g-force during whatever it is, whether it's acceleration or braking or cornering or bumps. And I didn't honestly know what to expect here. And so I really just wanted something, not anything incredibly accurate, but just something that I could go off of, like a reasonable number, and base my math around that. So in the interest of science, I wanted to look into it, and I could have probably Googled around to find something reasonable or in the ballpark. I might have been able to mimic the existing part in SolidWorks with the same material and try to meet those same strength requirements. But there's a third option, and that's using a live experiment. And that's the one that I'll be going with strictly for scientific purposes and not because it's more fun. So here's a quick clip that I've prepared for you guys where I went ahead and tested this. So here we are in our laboratory today. We've got some lab assistants here. Okay, never mind, they're running away. So anyways, here we are in the laboratory, and what we've got going on might be just one of those ideas that was so crazy it could actually end up working. So to give you guys an overview of what we've got here, I have my phone sitting perpendicular on this phone mount, which is relatively close to our headlight brackets. And then on my phone, I'm running an app that records the screen, and it's pulling the audio from the Bluetooth in my helmet. And what we've got going on the screen is an app that I downloaded that pulls the accelerometer readings from the iPhone. And so when we've got bouncing going on, it's going to read it, and the Y direction is going to be basically straight down. So we've got 1 right now for just regular gravity, and as we hit bumps and do stuff, that's going to increase. Oh, the GoPro may not translate it, but because it's got that really good image stabilization, but this is painful. Never tried to aim for the bumps before. I'm not hitting that one. Sorry, guys. Alright, yeah, so we should have got some decent readings out of that. There's a few more. So let's go ahead and I'll take a look at those later, but I'm going to continue on. So here we are on a conveniently closed and straight road. And let's test what's probably the worst case scenario, well, aside from crashing. We'll just call it abrupt acceleration and deceleration. Let's do them at the same time. Yeah, I think that's a pretty good spike, 5.6. Next on the list was to collect some G-force data during cornering, which I did. I just made a few pit stops and ended up collecting data for quite a while. So here's a quick montage of that data collection, we'll call it.
Y'all come on in now. Come right on down front. I got something I want to show you. Now y'all heard of the popcorn? Y'all heard of the dog? And you heard about all of them other dances. But now there's a brand new dance that's going around. I want to show you exactly what I'm talking about. I'm talking about the funky chicken. Y'all ready? I say y'all ready? Okay, here we go. You raise the left arm up and your right arm too. Let me tell you just what to do. Start both arms to clapping, start the beat to kicking. That's when you know you're doing the funky chicken. Second spasm. You put both arms up across your face. Your knees start wiggling all over the place. You flap your arms and your feet start kicking. Then you know you're doing the funky chicken. Hey, hey.
So I hope you enjoyed that science experiment as much as I did. But coming back to our math slide now, we've got some data to input. And so finishing this thing up, I weighed my headlight assembly, which I'll round up to about 6 pounds or 2.7 kilograms. And after reviewing the footage and the accelerometer readings, There was increased acceleration, again, upwards and to the sides and downwards, but just going to focus on the downward acceleration for the sake of the webinar. And the highest I saw was about 6 Gs downward during the abrupt acceleration test. And so it's awesome to have that real world data now and a decent range to sort of base my inputs off of. But with that said, I know I could probably still push those numbers higher, and I don't want to design something that's just strong enough. I want to add a big safety buffer here on the front end because, again, I know that testing wasn't 100% thorough, and there could be worse bumps or situations I put myself in. And so that 6 Gs is good, but I'm going to round up to 10 Gs just to be safe. So when we take that 10G acceleration and plug it into our formula, we come up with about 132 newtons, which is 30 pounds force in freedom units. So coming back to what we need for our simulation, we have our fixed points, and now we have our force and its direction, but we're still missing a pretty big piece of this puzzle, which is the CAD model and the sliced file. But fortunately, this is a relatively simple part, and I already have an existing part to go off of. So the design is nothing too crazy, and there's not a bunch of fancy tricks I need to use. But there are a couple of considerations I have going into this. And we talked about the main one earlier, which is I want to switch up how the windscreen is mounted. And related to that is that I want to use all of the original hardware, which is spacers and bolts. And that means keeping the existing spacing of the bolt from the thread. And the reason I want to do that is because if I ever sell this bike, I want someone to be able to switch back and forth between the old bracket easily. I know what I'm doing won't be everyone's cup of tea. And so keeping the old bracket is one thing, but the last thing that I need are more random nuts and bolts floating around. And on that same topic, I don't mind using extra hardware in the design because I have a lot of random nuts and bolts floating around. So uh, that's problem one. And two, and to sort of solve both of those at the same time, I'm just going to switch the way that the bolt goes in. So I'm actually going to have the bolt come in from the outside, and I'll just put a thread or a nut on the inside. So the third and fourth things here are also related, and that's that I want to make this thing smaller if possible. And to do that, I'd like to get rid of the existing curve that's in this thing and sort of sink it all in towards the headlight a little more. And I can even absorb these spacers like into the part if I need to. And another benefit that I get out of doing that is fiber is much stronger when it's in the same layer together. So if I've got this bend, I can start putting fiber in, but it's only going to be in this, beginning of this bent part, and it's not up until, more towards the middle where I can fit fiber within the same layer. Because I'm going to be printing it in this orientation here. And so it just helps out if I can get this thing a little bit flatter, and it will also give me more of the aesthetic that I'm going for. So I'm sure we've got a lot of SolidWorks experts with us, so I don't want to go into all the details here, but this is what I came up with for just Rev A, just my first shot at this thing without any simulation results or anything. Uh, and there's not a whole lot of crazy stuff going on here, but I did want to show a couple of the things that I did. I'm sure there's different or better ways to do this, but to locate the holes, I kind of built them around this XY coordinate system and used my dimensioning based off of that. And then I created this really simple part that's super small. I think it took, maybe 5-10 minutes to print this thing. And I held it up to the existing part, and I could tell where the holes were. And maybe my trusty Harbor Freight calipers weren't as exact as I wanted them to be, and I needed a couple of millimeters in certain directions. And so using my XY coordinate thing, I could just sort of move these around and shift them as I needed. It was pretty close the first try, but I did need to make a couple of minor adjustments. So it was kind of a convenient, quick way to do that. And then from there, ended up roughing out the rest of the shape. Nothing too crazy, but the other convenient thing is that because it's symmetric, I could just mirror this. And so that's what I did here. And to save just one of these, you can actually conveniently do this from the same menu where you're saving it as an STL. So I select the file type. I'll go ahead and replace it, no big deal. So the first thing it asks you, yes, you want to save it. But the second thing, selected bodies, because I just clicked this right bracket before I went to that save menu, I can select this option and it's only going to save that body off into the STL file. So I can do the same thing for this other bracket and that'll work just fine. So now we finally have our CAD model. We have all the forces we need. And so we can bring it into our slicing software and start calculating and simulating the forces on this part. So brought it into Eiger, laid it out. I selected the materials I want to use, which is onyx. That's a nylon 6 with chopped carbon fiber. And I wanted to reinforce it with a secondary continuous carbon fiber. I left everything else as default, so my layers and my infill pattern and shape and density. But I did go into the X-ray view. And for my first shot at it, I did what we typically do, which is laying out a sandwich panel. So on the very bottom, I've got this layer of fiber that's completely filling the layer and rotating to give it strength kind of uniformly in different directions. And then in the center, I used one group of fiber that I just striped out. And so I knew I wasn't going to need to fill this entire thing full of fiber. So striping it allowed me to put a couple of these just little groups of fiber. And these ones are just concentric. So it's only going around the outside and reinforcing those holes. It's not fully filling the layer. And then I repeated my full sandwich panel at the top of the part here. So once I set all of that up, I went over to simulation. I was able to select these faces to anchor my part. And then I was able to select this face to put my force on and select its direction and enter in the value of that force. And what I realized was that I very much over-engineered this first one, which is always a good thing. And to take that even further, once I ran this simulation, it validated where it was. It kind of showed me this exaggerated report of where and how this thing was bending. But it also, once I finished running it, I ran an optimization. And optimization runs a bunch of different scenarios. And what I found out was I could run this thing in only Onyx, and I'd still have a pretty high factor of safety of 3 and only a minimum deflection of 0.24. With no fiber layers, and this thing would drop the price significantly. So based on what I'm looking for, like if I'm looking for something super fast, I might go down to this 9-hour option. So it's just cool that I can spit these out and get a view of all of them. But what I got out of it was that I could shrink this thing down and make it look much better. So that's what I did. I hopped back over to SolidWorks, thinned it out, and now I've got this part, which is half as thin. And I probably could have kept going here, but I ran out of room for thinning it out because I still wanted these sort of embossed little holes for the bolts, and I didn't want to have to change the hardware or use a bunch of supports under this to make it thicker or thinner. So left it at this, laid my fiber out similarly, but much fewer groups and much fewer stripes within those groups, and then simulated this one as well. And I was still able to get a super solid, 3.29 factor of safety out of this with a maximum deflection of 0.17 millimeters. So I was able to drop the part cost down from $48.42 to $20.30. I was also able to drop my print time from 12 hours and 7 minutes to 6 hours and 23 minutes. So this simulation software saved me a ton of time and a ton of money, and it made my part look much better. So I was really happy with that. And the next step was, of course, moving on to printing and testing the part. So once you've done everything else on the front end, the printing and testing part is very easy. So not too much to talk about there, but printed them out, was happy with the way that they looked. And before I put them on the bike, I figured I'd put them through a little bit of a test. So I made a very sketchy jig here where I just bolted it to just a piece of wood that I had. And I was able to hang 45 pounds from this thing with no deflection. I ran out of space and weights to keep testing. And I also even tested it in the orientation that I was sort of more worried about. And I was able to hang 25 pounds from it. I could have probably gone much further. It barely even bent from this 25 pounds. But I went ahead and played it safe. I didn't think I was going to get much more force than that from riding. So from there, I went ahead and installed it onto the bike. And it was such a good feeling knowing that this was the last time I'd have to pull this headlight assembly apart completely and juggle all these different parts. And so overall, just thrilled with the way that this thing turned out. I like the way that it looks, and functionally, it does exactly what I wanted it to do. These bolts are super easy to take in and out, and the big hole in the center even helps me get my fingers back there where the nuts are on the other side. So much faster and easier to replace. And I have full confidence that I can go around riding and do whatever I want, and this thing is going to hold up to everything I can throw at it. And with that, we are at the end. So, really appreciate you guys sticking around. I hope that you found this entertaining and informative, and you were able to see some of the uses for simulation in general, but also specifically 3D printing simulation and where it can be extremely useful, especially with our Markforged Carbon Fiber printers. So, thanks again for sticking around, guys. I had a lot of fun making this one and would love to make more projects if this is something that you're interested in. So definitely let us know. But in the meantime, we'll go ahead and we'll stick around and we'll try to answer any questions you may have.